Look at this digital globe. For a multinational enterprise, the objective is to channel vast datasets into a central hub to train a high-performance, enterprise-grade AI. But as you can see, those data streams are crashing at the borders. Strict data sovereignty laws enforce these boundaries. Across the globe, regulations now mandate that raw customer data must remain locked within its country of origin. For a large-scale enterprise, this creates a severe operational deadlock. Because the data cannot be legally extracted, the corporation is effectively fractured into disconnected local workshops, each working with a narrow slice of intelligence. The traditional model of moving raw data into a central server is no longer viable under modern global compliance requirements. To bypass this deadlock, the architecture must invert. Instead of moving the locked data to a central model, the enterprise moves the computation to the data. This animation illustrates a mechanism called federated learning. Federated learning is a decentralized training method where a shared model is updated without ever exchanging the underlying raw data. Headquarters dispatches an initial AI baseline model directly to its global branches. These baseline models are locally fine-tuned using the locked data. The AI learns directly from these regional vaults, analyzing customer behavior and extracting patterns, without the raw information ever leaving the premises. When training is complete, the regional branches send back only mathematical weight updates, essentially the learned skills. These weight updates are numerical representations of model adjustments that contain zero raw data. By circulating knowledge rather than files, the enterprise synchronizes its global intelligence while strictly honoring local data sovereignty. However, transmitting these mathematical updates across the open internet introduces a significant security exposure. This shows a gradient inversion attack. A gradient inversion attack is a sophisticated exploit where an interceptor analyzes the weight updates to reverse engineer and reconstruct the original sensitive data used during the local training session. To neutralize this, the system employs privacy-enhancing technologies. The first layer, differential privacy, injects mathematical noise into weight updates before transmission. The second layer, SMPC, shatters that noisy data into fragments, distributing them across network paths so no intercepted packet contains a complete picture. These technologies decouple the model updates from the original identity of the data, bringing the risk of reconstruction down to a negligible level that meets rigorous regulatory standards. Securing the data is only one challenge. Large language models have heavy processing requirements, yet multinational companies rarely have identical hardware in every international office. Forcing a complex model onto a small regional server with limited power will overwhelm the hardware and stall the local network. This diagram illustrates FlexLoRa. FlexLoRa is an algorithm that dynamically resizes the AI training matrix to match the specific hardware capacity of each local node. A regional hub with top-tier GPUs can calculate deep features, while a smaller office processes a lighter version. Every location contributes intelligence within its specific physical limits. Dynamic hardware scaling turns global hardware variety into a flexible, inclusive asset. The final hurdle is network latency. In a standard setup, a single slow connection creates a straggler effect, forcing the entire global headquarters to wait for that one region before it can update the central AI. The solution is HGFL, or Hierarchical Global Asynchronous Federated Learning. As you can see, HGFL allows the central hub to integrate updates as soon as they arrive, rather than waiting for every node to finish at the same time. Headquarters merges data streams in a rolling cycle. This ensures the central AI model iterates and improves the moment a regional node finishes its work. Asynchronous aggregation removes global wait times, allowing the enterprise AI to evolve at the speed of its fastest contributors. This fully optimized architecture shows a system running with high efficiency, integrating federated computing, secure encryption, and asynchronous scaling. The initial paradox is resolved. The enterprise has built a globally intelligent AI without ever centralizing a single byte of raw customer data. The system leverages the collective intelligence of every branch worldwide, driving high operational efficiency while maintaining a verifiable technical barrier between raw data and the global model. Enterprise intelligence now scales through secure, federalized sovereignty.